Gunn, who's a student here at UC Berkeley, and he's also here wearing the inverse of that sweatshirt, so you can find him. And so I'm going to first present a very general framework for watermarking any generative algorithm, and then later I'll show you specifically how we instantiate it for LLMs, because that's what this workshop is about. And so for now, I'll talk about this very general template where you have some generative algorithm, or really any randomized algorithm. This is represented by this robot. And this algorithm takes as input some randomness, and then an actual input or prompt, and then generates some content. And as Scott mentioned, these algorithms really use their randomness to create a wide variety of outputs. And so this randomness is especially important for watermarking. In particular, most watermarking schemes, including ours, work by modifying this randomness. And part of the reason for this is that these generative algorithms are extremely expensive to train. So we really don't want to change them. Instead, we want to just make a minimal modification to the randomness and hope that the content's quality is not degraded. Okay, so if we're going to modify this randomness to embed the watermark, one thing we might hope to do is replace it with some kind of more structured, tampered randomness. So if before our algorithm took as input, say, a uniform binary string, we could instead replace this by a random string that's biased heavily towards all ones. And now we could hope that some of the signal will show up in the content. And it turns out that there is a randomness recovery algorithm for nearly every generative model that we know of that takes the content and outputs something that's similar to the randomness that was used to create it. So if we changed our randomness to be heavily biased towards ones, then we can generate this content, do randomness recovery, and then observe this bias to detect the watermark. But there's a problem here. In general, just arbitrarily tampering with this randomness might hurt the quality of the content that it outputs. For example, if you were to do this with an LLM, this might result in the LLM favoring certain topics or words, which is undesirable. And so we want to be very careful with how we tamper with the randomness. And thankfully, since we're cryptographers, we can use indistinguishability to argue about quality. So let me tell you exactly what I mean by this. We know that if no polynomial time algorithm can distinguish between the watermarked algorithm and the original algorithm, then this means that in particular, any reasonable quality metric that you could actually evaluate efficiently will be the exact same on the watermarked model as it was on the original model. And you can formalize this using an experiment, which we call undetectability. So you can imagine some efficient distinguisher interacting with either the watermarked model or the original model. It doesn't know which. And it can ask the model some prompts and get back responses. In particular, it can do this adaptively. So based on previous responses, it can carefully craft its next prompt. And at the end of this game, the distinguisher needs to say whether it thinks it was interacting with the original model or the watermarked model. And in previous work with Sam and with Zamir, we defined undetectability to be the property that no efficient distinguisher can tell the difference between the watermarked model and the original model. And so the watermarks that I'll talk about today satisfy this very strong notion of quality. Okay, and now from cryptography, we know that you can replace a random string with a pseudorandom string, and this indistinguishability property will be satisfied. So we can go back and choose our tampered randomness to be some pseudo-randomness, and now we can do the same thing as before. Generate some content using this tampered randomness, and then run randomness recovery to see if what we get back is pseudo-randomness. But since now we're using pseudo-randomness, this detection will have to be with the trapdoor. So now we've achieved the quality guarantee that we want, but there's a secondary problem. Oh, sorry. First, okay, I'll spell this out just a little bit more. To embed the watermark, importantly for each query, you're going to generate a fresh pseudorandom string. So we're not using the same pseudorandom string each time. It's very important for the pseudorandomness to be independent for each generation to avoid introducing correlations between responses. So for each query, we're going to draw a fresh seed, apply a pseudorandom generator to the seed to get a pseudorandom string, which is going to embed the watermark signal, and then we generate some content using this. Now to detect, all we need to do is run randomness recovery and see if what we get is a PRG output, which requires this trapdoor detector. Okay, so now the problem is that randomness recovery is actually only approximate in practice. So we don't get back exactly this random string that was used to generate the content. We only get something that's similar to it. And for the trapdoor pseudorandom generators that we knew how to construct before this work, the trapdoor only works if you're given exactly a PRG output. So the object that we need now is what we'll call a pseudorandom code. It's exactly a trapdoor pseudorandom generator with a robust decoding algorithm or detection algorithm. So this means that if you're given something that's close to a PRG output or close to a pseudorandom code word, then the detector can still tell. And we actually construct an even stronger object, which has a robust decoding algorithm. So what this means is you can actually encode a message in the pseudorandom code word. And now, even if that message, or even if that ciphertext is subjected to noise, the decryption algorithm still can recover the message. Any questions about this framework? Okay, and yeah, I'll just reiterate that this is a new cryptographic object that we constructed in this work. Okay, so now that I've told you sort of at a very high level why we want pseudorandom codes, I'll show you what they actually are and how we construct them. So a pseudorandom code consists of an encryption algorithm and a decryption algorithm, and they must satisfy two properties, pseudorandomness and error correction. And pseudorandomness says that code words must appear random to a computationally bounded distinguisher. This is like CPA-style pseudorandomness. And then error correction, as you might expect, says that you can decrypt even if the ciphertext is subjected to some noise. And importantly, we want this decryption to be robust, even if this is a constant rate of noise. So even if, say, 49% of the bits in the ciphertext are flipped. And for the purposes of this talk, I'll consider only binary PRCs. So the ciphertexts are binary, and I'll consider only random bit flips, but in the actual paper, we do consider other error models. And I'll also mention that we construct a stronger notion of public key pseudorandom codes in the paper. So here you can encrypt with a public key, like public key encryption. But for this talk, I'll focus on the secret key setting, where you use the same secret key to encrypt and decrypt. Okay, so how do we actually construct these? The first natural thing you might try is, we have pseudorandom encryption and we also have error correcting codes. And so you might try to combine them in some generic way. But the two obvious ways that I could think of have their own problems. So first, you might try to take your message and apply an error correcting code. Now this is robust, but you want it to be a pseudorandom ciphertext, so okay, you just encrypt that. But now you've lost all of the robustness that you gained from the error correcting code. On the other hand, if you first encrypt your message, now this is pseudorandom, but if you apply an error correcting code on top of this, this will in general introduce a lot of structure. And so it's not obvious how you can choose an error correcting code to preserve the pseudorandomness of the encryption scheme. And the problem with both of these approaches is sort of that you need every bit to satisfy both pseudorandomness and robustness simultaneously. And it's not clear how you can sort of combine an error correcting code and encryption to get both of these properties at the same time. Okay, so we started from scratch and observed that, thankfully, a very standard cryptographic assumption, learning parodies with noise, is an assumption about the pseudorandomness of error correcting codes. In particular, it says that if you have noisy samples from a random linear code, they are pseudorandom. So if A is a random matrix, then if you have AS plus E, where S is uniform and E is some low weight error, this is indistinguishable from a random A and a random string U. Okay, so if we want to encode just one bit with this, you could think of encoding 0 by outputting a random string and encoding 1 by outputting a noisy random code word. And so LPN says that this is pseudorandom, which is nice. But unfortunately, LPN also says that even if you know this matrix A, you cannot distinguish between encodings of 0 and encodings of 1, because doing so would break this indistinguishability. So this is a good starting point for pseudorandomness, but in order to actually decode efficiently, we're going to have to do something new. And our idea here is to sample A along with some extra trapdoor information that allows exactly for this efficient decoding. More specifically, what we do is we sample first a sparse parity check matrix P, which looks like this. And very importantly, each row of P is going to be log n sparse. And I'll show you why this is important in a minute. And this P is going to be our trapdoor. So now when we sample our generator matrix A, we're going to sample it subject to the constraint that PA is equal to the all 0 matrix. Yeah?
And here, is that the number of tokens, or is it like a security parameter, just like a...
Yeah, you should think of it as a security parameter. So n is going to be the code word length, and then when you actually go to embed the watermark, if you want to allow for a longer response, then you can sort of embed code word after code word after code word.
And R is like some parameter that's determined from n, from the LPN assumption, right?
Oh, sorry. R will be the length of the code word. N is the security parameter. No.
The same.
Okay, it's not super important.
Maybe.
R and N are like linearly related, so they're essentially the same thing. One of them is the security parameter, the other is the length of the code word.
Yeah.
Okay. And so we sampled this trapdoor to have the property that PA is equal to 0. And I want to point out that here what you also get is if you have a noisy code word AS plus E, then P times that is going to be equal to P times E. And if E is low weight, then since P is sparse, then PE will have significantly lower weight than you would expect for P times a random vector. And this is exactly what will let us decode.
Could you, just in a couple of words, elaborate how just roughly, like, in what way does this improve over Scott's construction that you use black box PRG?
Sure. So I'll show later in more detail that this achieves robustness to a constant rate of errors. So for Scott's scheme, you were taking these k-grams, and it was important for quality that the k-grams don't repeat very often. And so if you want high quality, you need to take k to be greater than some constant asymptotically. And so now if you change 1 over k of the tokens, you'll lose the watermark signal entirely. Whereas here, we can accommodate any constant rate of errors. Okay, and so now remember we wanted to apply LPN to say that noisy samples from this code are pseudorandom. But we've sampled A in this completely different way. Before, A was random. Now A is sampled to be consistent with this trapdoor. But fortunately, we showed that if you do our sampling process and you choose parameters carefully, then A will actually be statistically close to uniform. And I'll point out that because of these parameters, we need to rely on subexponential LPN. Okay, so just to spell out the whole construction, what we're going to do is we sample this P at A, and now to encode 1 bit, if we want to encode 0, we output a random string. If we want to encode 1, we output a noisy random sample from this code. And now this code word is going to be pseudorandom exactly by our theorem and by LPN. And to decode, you take your secret parity check matrix, you apply it to the given vector, and you check the weight. And now if this was a random sample from our code, then this will have weight significantly less than the dimension over 2. On the other hand, if this was an unrelated vector, then the weight will be roughly r over 2. So this lets us decode efficiently. And this holds if the error has constant weight, and so this is why we can tolerate a constant rate of errors. Okay, and so what I've shown you before is just how you can encode a single bit.
I'm just trying to find the secret key. It's the P.
Yeah, the secret key here is P.
And okay. And it was used in the encoding.
So we used P to sample A.
It's the low density thing. Okay.
Exactly, yeah. And so maybe I'll also point out the reason why we also get a public key PRC is because here you might notice encoding only requires A. And because LPN says that you can publish A and still have pseudorandomness. This is also a public key PRC. Yeah, and of course the decoding algorithm needs to know the trapdoor P. Okay, so what I've shown you so far only lets you encode 1 bit, but I promised you that we could encode longer messages. And there is actually a way to do this that is more efficient in terms of the rate than just concatenating these 1-bit code words. So what you can do is you can sample lambda random bits, U1 through U lambda, and use this concatenating 1-bit code words to encode these bits. And now you can use them to seed a PRG to get a one-time pad that you apply to an error-correcting code applied to your message. And so here, this inherits the error correction of this generic error-correcting code that doesn't need to be pseudorandom. And it also asymptotically inherits this error-correcting code's rate. So for very long messages, this actually achieves linear rate if the underlying error-correcting code has linear rate.
Sorry, what goes wrong with the message instead of U1 through U lambda? Like, do you need them to be random?
The message might be very long. So it would still be pseudorandom, but you don't get the improvement in the rate. So our main result in terms of our pseudorandom code is that we construct it assuming subexponential hardness of LPN, and it has linear rate, and it's also robust to any constant rate of worst case bit flips. I have an asterisk here because it's a little bit of a weird definition of worst case. Noah will show you a bit of a stronger notion of worst case robustness in his talk. And we also are robust to random deletions. I won't talk about this today, but it's in the paper, and I'm happy to talk about it more offline.
What about insertions?
Random insertions we can also do, but they have to be random. And we don't mention it in the paper, but it's the same construction as for the random deletions. Works for random insertions.
But presumably not rearrangements, like moving a paragraph from one place to another.
So if you move a chunk of text that contains an entire code word, then we can still detect there. But if you move smaller chunks and sort of scramble the code words, then we can't.
Thanks.
And just like, we don't need to go into the asterisk, but like the worst case is statistical, but the rest of the construction is computational, or the worst case is also computational?
The worst case is statistical, but the weirdness is that sort of the errors need to be chosen before observing any code words. Yeah, I guess I'll also say that Sam, Yevgeny, some other co-authors and I have an ongoing work where we show a stronger kind of worst case, computational worst case robustness, where you can observe code words before making errors, but now you're computationally bounded in making the errors. Okay, so a while ago, I showed you this watermarking template, and now we've constructed these pseudorandom codes so we can actually instantiate this watermark. Now we have these. Okay. And I'll mention that our template immediately gets us some nice corollaries. So the first is that robustness of our pseudorandom code translates immediately to robustness of the watermark. So imagine you have some content and you modify it in some way. then if the randomness recovery algorithm behaves nicely, and this translates to similar errors in the recovered randomness, then the robustness of the pseudorandom code can recover from those errors. And it turns out that the randomness recovery algorithm does have this nice property both for LLMs and also for image models, which I'll show more in depth later. So by designing more robust pseudorandom codes, you immediately get more robust watermarks. And since our pseudorandom code is robust to a constant rate of substitutions, our watermark also is. And then the fact that our pseudorandom code can embed messages is also quite useful for watermarking. So first, you can imagine you want to embed some additional metadata in the watermark, say like the version of the model that created the content, or like a user ID or something like that. And so because we have these linear rate PRCs, we can do this like asymptotically efficiently. And a more interesting application of embedding messages is something called public attribution. The setting here is that there is a public detection key that might be used to attribute harmful content to a model that generated it. So here it's very important that this is unforgeable. You don't want to be able to like forge a watermark on some harmful content that you yourself generated. And so you need some notion of unforgeability. And it turns out that by embedding a signature as the message in the pseudorandom code, where the signature is like a signature of part of the response output so far, you can immediately get public attribution from our PRC watermark. And so there are more details about this in our paper. Maybe I'll also say that we can have a sort of dual mode watermark, which has a single embedding algorithm, but two detection keys, one regular, like standard watermark detection key, which is robust, and another public attribution detection key, which has this unforgeability property. So yeah, you can see the paper or ask me about this later if you're interested. Okay, and so now I will sort of spell out this framework for large language models specifically. And Scott already mentioned this a little bit. These language models work in an autoregressive way. So they'll keep outputting tokens, and for each token, they'll first compute a probability distribution over it using some underlying neural network. And now they'll sample a token from this distribution and output it, and continue doing this until it reaches some special done token. And so our watermark and others modified this sampling process. Once you've done the watermark, like the user's interaction with the model is essentially the same. So it can still, query a prompt and get back some tokens. But the watermark adds this detection algorithm where, given some key and given some text, you can determine whether it's watermarked. Okay, and typically these watermarks will change the sampling process according to some secret rule. And here, like the secret key will describe what the secret rule is. So the way that our text watermark works is, again, just by modifying the sampling process. And what I'll do is first describe an equivalent way of thinking of the standard sampling process that a regular LLM uses. And then I'll show you how we modify it to embed our watermark. So you can think of an unwatermarked LLM as sampling from its probability distribution as follows. For each token, it has some random bit ki. And so for the ith token in the response, what it can do is it can first compute the probability distribution over the next token. And now it can look at its random bit ki and increase the probabilities of the tokens that hash to this bit. And now sample from this modified distribution. Okay, and so it might look at first like I changed the distribution by forcing the model to sample a token correlated with ki. But because the ki's are random, this is actually statistically the same as just sampling from this distribution. And sort of the intuition is the ki's are random bits. So half the time you're increasing the probability of tokens that hash to them. The other half the time you're decreasing. And so in expectation, it's the same. Okay, and so I have not modified the sampling process if the ki's are actually random. And so if you replace them with pseudorandomness, in particular with the pseudorandom code word, now this whole process is computationally indistinguishable from the original one. And you'll also notice that the hash of the token that we sample has some correlation with Ki. Like more than half the time, it will be the same. And so because our pseudorandom error correcting code is error correcting, if you get a watermarked response and you compute the hashes of the tokens, then the string that you get back will be equal to the original KIs that you embedded on significantly more than 1/2 of the entries. And so now our robust detection algorithm will output 1. Okay, so here we exactly replaced the randomness that the algorithm used with the pseudorandom code. And in this way, we were able to watermark the text in a way that was quality preserving, in that our watermark is undetectable. It's computationally indistinguishable from the original model. And also because our pseudorandom code is robust, our watermark is robust to a constant rate of substitutions.
Sorry, to which constant rate? Like up to 1/2 or something like that?
Yeah, so you pick any constant less than 1/2, and then you can set the parameters of the code to achieve that robustness. Yeah. Okay, and so there have been many works on watermarking that achieve different trade-offs between quality and robustness. As I sort of mentioned earlier, with the hashing k-grams approach, you'll be trading off the length of the k-gram, which gets you, like, longer length is better quality, but lower robustness. And this pseudorandom code approach sort of breaks out of this trade-off by having, because the PRC is error correcting and pseudorandom at the same time, you don't have to trade off this k-gram parameter. And so we achieve both comparable robustness to these existing works and also the strongest quality guarantee achieved by any of them. Okay, and as a sort of last and sort of tangential point, but also very interesting, I presented this general watermarking framework and just talked about it for LLMs, but it works for other kinds of generative models as well, in particular for image models. So in a very new work by my co-author Sam and also Xuandong, who's here, and Don Song, they showed that you can use pseudorandom codes to watermark image models in a very robust way. And so the idea is the same template. You are going to take the randomness used by the image model and replace it with the pseudorandom code. More specifically, these image models work by choosing a random vector in some latent space and then running a sort of generation algorithm to translate this vector into an actual image. And so what they do is, instead of sampling a random Gaussian vector, they sample it conditioned on the signs matching the bits of a PRC code word. And it turns out that there's a very robust randomness recovery algorithm which takes an image and maps it back to the latents, which recovers the signs very well. And so they show that if you embed a PRC code word in the signs, then you're actually robust to a very large class of attacks, sort of the typical ones considered in existing image watermarking works. And also they show that according to the standard quality metrics for image watermarks, their watermark has the highest quality of all of them. So I want to emphasize that pseudorandom codes are not just like an interesting theoretical object, but actually they were able to show that for image watermarks, they give a very practical watermark as well. And yeah, they're here, so you can ask them more about their work. Okay, so what I've shown you is we constructed this cryptographic primitive, a pseudorandom code, which you can think of as pseudorandom encryption with a robust decryption algorithm. We were able to construct these using standard cryptographic assumptions, in particular subexponential hardness of learning parodies with noise. And our PRCs have linear rate and also are robust to any constant rate of random substitutions and deletions. And using these PRCs, we were able to instantiate this general watermarking framework. So It seems that they are a natural tool for hiding information in the outputs of any randomized algorithm. I'd be very interested to see PRCs used to watermark more things. And the robustness of the PRC very nicely translates to robustness of the watermark that you get. Okay, so thanks everyone for listening, and I'm happy to take questions.
In terms of the assumption that you make, do you know as a PRC is a primitive, or does it imply LPN?
No. So yeah, we know very little about how PRCs as a primitive relate to like existing primitives. I think that's a really interesting question. We don't know how to build them from one-way functions.
Know that they imply one-way functions.
Oh, they imply one-way functions. Yeah, because they, yeah. Yeah, but we don't know whether they imply LPN.
Could you say what the randomness recovery algorithm is for LLMs?
Oh, yeah. So in the example I showed, which is not exactly what we have in the paper, we take the hash of each token in the text. This gives us a binary string. This is our randomness recovery.
I see. Okay.
So for text, it's very simple. It's just basically take the text that you have and convert it to binary. In the actual paper, we describe a process to turn the whole LLM into an LLM that outputs a binary response. And so there, the randomness recovery is even simpler. It's literally just take the response.
So suppose that everything was offset by 1 because someone, inserts a word or deletes a word. Like, what happens then? Just to help me understand.
Yeah, so this scheme does not detect the watermark. Now, if you suspect that the text was offset by 1, then maybe you can test all offsets. That's a bit cheating. So we're not robust to shifts in that way.
That'll be the next talk.
That'll be the next talk.
Got it. Thanks.
You want to do the introductions for the next talk?
I guess this is more related maybe to the image work, but what happens if you compress an image and decompress it?
Just depending how much you compress it, it'll work. Yeah, for like reasonable compressions, you should see the paper. There's example pictures where like if you compress it so much that the watermark disappears, then you noticeably harm the image quality. I would say that's the highest sort of bit. Is just to remove the watermark, you have to noticeably degrade the quality. Yeah.
And so just to play devil's advocate, what happens if you try and do fill in or something, or like sharpen it through super resolution?
I don't know, Sean, you know what that is?
We conduct different modification. So as long as the semantic information, so the image watermark will go over a VAE structure, so it's still with the latent code. So if you do super resolution, the latent code won't change too much.
Okay.
So, but that statement you just made, that in order to remove the watermark, you have to degrade the quality. Like, that's an empirical statement.
I guess maybe I should say, yeah, that's an empirical statement.
Yeah.
You should see the paper if maybe decide for yourself whether you believe it.
All right.
Yeah. But that was at least my takeaway from the experience we did.
I had a question in terms of practicality. So at some point, we tried different parameters, and we struggled to find parameters that made it practical to detect this. Do you have guidance on which parameters should be selected to have something that can detect less than 1,000 tokens, or because in my experience when I tried it, it took in order to manage more tokens to detect the watermark than schemes that harm the quality a little bit more. Basically, have you been able to make the text version of this practical, or is it still a little bit impractical?
Yeah, the text version of this we have not been able to make practical, and that's because of our actual PRC construction. So by constructing a better PRC, conceivably it could be very practical for text. We don't know how to construct that PRC. And so I would say for text right now, it's more of a proof of concept, where if you do have a long enough text to embed a code word, then for that text, you get very strong robustness. But the actual length that you need because of our concrete parameters is long compared to other schemes.
I was wondering, I mean, the scheme has a lot of really cool properties. It would be possible to like give up on some of the indistinguishability in some way, maybe make it less indistinguishable, but to allow to have something that's more practical. Like, for instance, the Kirschenberger scheme, right, which adds deltas, which is not injectable, it's more efficient. If you could basically do some sort of hybrid where you get your nice guarantees, but also something practical by giving up on like maybe your notion of like your current notion of like indistinguishability.
Yeah, so our analog of that would be to take sparser parity checks, which you could do. And I think still the amount of text that you need is quite long. So to make it practical, I would really expect you to need to come up with a new pseudorandom code. But I don't think it's out of the question. Yeah, and I guess I'll also say for the image watermark, actually, they took the parity checks to be quite sparse to sort of push that trade-off. And they were able to show that even with very sparse parity checks, they had the highest performance on the actual practical quality metrics.
Yeah, I looked at the image papers. Really cool.
So my understanding is that for images, a lot of the cutting edge models, they use diffusion. They start with a random input, Gaussian input, and they apply a neural net, add it to it, add more noise, and it's this process that has many steps. And it sounded like the type of model discussed in this work you mentioned, it was like just a one-step thing, right?
No, this
started with the.
It's for stable diffusion. All the experiments in that paper are stable diffusion.
Awesome.
It turns out randomness recovery works surprisingly well for diffusion models.
Could you say a couple of words how you do it?
It's basically, I mean, it comes from this paper of his, I guess, tree rings, where was the first one, I think, to use like a diffusion inversion. Basically,
When is the first one to do diffusion inversion?
Sorry,
Or the first one to use it for watermark.
For watermarks. Sorry, that was a key important 2 words to say. But yeah, I think, it's just, there's an algorithm that you can use. Basically, it's just the reverse of the diffusion process. It turns out, at least especially for like DDIM, which is like the deterministic diffusion version of diffusion, it works very well. There's other versions that work for DDPM, like the probabilistic diffusion version. I guess the reason for these is that people want to be able to map between images and latents for like image manipulation in the latent space. So that's why it was already like a thing that exists, and then the tree ring watermark was the first to use this for watermarking, and then we're using the same kind of thing.
Does this mean that it would be easier to maybe go from the proof of concept for text to a diffusion LM rather than autoregressive LM?
Are you saying you could use it for a diffusion LLM?
Yeah, because you're saying that it's like difficult to judge for autoregressive text and just in text it's harder. So do you think just doing it on diffusion LMs or something? Like mask filling?
You could imagine. That could be. One could try that. Yeah, we didn't try that. I think.
Do you know if there's a way to go from the text back to the latents?
Yeah, I don't know. I've tried it once for privacy purposes, and it was very hard. So I don't know, because it's the whole discrete continuous thing. But it would be interesting to do that.
So I'm just curious, what happens when you screenshot an image? You get exactly the same pixels back? So you put the image up on a screen and you screenshot it?
That's not going to matter. Yeah.
That's not going to matter. And I guess you could take you could take a picture of that. Well, it's going to degrade quality, but maybe not as much as compression. I'm just curious as to what you tried.
I mean, no, we didn't try that. We tried maybe sometime just.
So we tried a bunch of attacking, like adding different noise, using blurring and other, like adding noise.
So you're doing this digital transformation.
Yeah, they're all digital.
Yeah, so
you didn't go to the analog world.
No, we didn't.
We didn't try that, but I assume that is also robust, because you do not change the content at all.
Yeah, but the pixels are going to come out very different, right?
So because we deal with the latent space, so after the VE, the latent space of that, even pixel level change a lot, then the latent level does not change too much.
You should try it.
Yeah.
I have a follow-up question. What about cropping an image?
I don't know if we actually tried cropping, would we?
Yeah, we didn't try cropping, but yeah.
I assume it just depends on how much you crop it. But maybe I wonder.
Yeah, so part of what I was also asking about the super resolution, like one thing that some of the image models are really good at is you can do in painting, just kind of remarkable.
Yeah.
Where I can literally black out some part of the image, and then I can fill it in a plausible way. And it's one of those things that I mean, then I could use a totally different model from the one which
Well,
you know.
So one thing that we did try, something related to that, is this like regeneration attack, right? So which is where you like add noise and then use a different diffusion model to remove the noise, which I think is very like morally similar to what you're saying, and it works quite well for that. But we didn't try that particular attack. I mean, I suppose really there's, you know, an infinite number of attacks you consider. It's definitely worth investigating more, but we only did like 10 of them or something.
Do you think that the right statement to like answer all of these concerns is something like, if, you know, because you guys are saying, softly saying something about, well, you know, the semantics are the same in the image, but then maybe these semantics are defined by the diffusion model that you use. So like, if in the latent space you couldn't distinguish, or, you know, they kind of map to the same place in the latent space, then everything that then it remains secure.
Exactly.
So it's kind of like, if you believe that, well, yeah, I don't know, the representations are good enough that they still capture the same semantics, even if you take a picture with your phone with the screenshot, then it stays safe.
Yeah, I think that's accurate. But although, by the way, that same statement would also apply to the tree-ring watermark as well as Gaussian shading. I think most image watermarks work in this framework where you're modifying the latents. So
I think people tend to imagine that the diffusion process scrambles the latents up a lot. And so if you modify the image, you're going to get back completely different latents. But the way that a diffusion model is trained is that you give it an image and you create latents by adding noise to that image, and then you train it to be a denoiser of those latents, right? And so you always have a very high correlation between the image content and the latents, just because it's trained to preserve that correlation. It's trained to create an image that has as much of a latent structure embedded in it as possible. And so if you can crop the image, you can shift the image, whatever, but the latents that you get back still sort of look the same. If you shift the image, the latents are basically also going to shift. But that's just because of the way that the diffusion models are trained. With a different image generator framework, you might not have that property. But some watermarks are weirdly, like unintuitively robust image degradations because of that. Next question.
Yeah.
Your encoder, I haven't had a chance to really look at the details of the encoder, but the encoder is not deterministic, right?
Right. Yeah, so for example, to encode 1 bit, what it'll do is it'll pick like a random, maybe I'll do that. Okay, so to encode 1 bit, it samples this random S and random error, and then it outputs AS plus E. So there's really like a lot of randomness.
Yeah. So this is a property of the encoder that I think is an overlooked thing. If you look at like the invisible watermark literature, an overlooked property of many of these invisible watermarks is that they actually make the sample completely deterministic. So if you were to sample from the same prompt twice, you would get back the exact same completion, which I think is bad from an industrial use case standpoint. I think that's bad. You could combine them with like other sources of randomness and other things to try to fix that problem. But I think the fact that your sampler is not deterministic is actually a big, I guess, bonus. Like it's an important property that I think is ignored by the watermark literature. But I think it's really good that you can preserve that property.
Yeah, that was one of the main priorities for us, is like not hurting the variability in the responses at all.
So crucially, this is included in the definition of undetectability, right? Like when we say undetectable, we mean you can interact with it arbitrarily, take many queries, and the whole interaction is indistinguishable. So this is so that's necessary for undetectability. We would definitely agree this is an important property.
So let's thank Miranda again, and let's take a break. We'll resume in a